This is our second lecture on electronegativity and molecule polarity. In the past lecture, we talked about how to determine whether a single bond is polar or nonpolar, and which side of the bond is partially or relatively negative and which is relatively positive. In this lecture, we're going to look at multiple bonds together to make up a whole molecule and how to determine whether the whole molecule is polar or nonpolar. And that has to do with where all of the partially negative atoms, how they're aligned symmetrically around the molecule, or whether they're asymmetrical. And if the molecule is indeed polar, we're going to look at what's called a dipole moment, which determines the direction that the molecule will line up in a magnetic field, and we'll look at a few examples of that. So again, just to review, a nonpolar covalent bond is when the bonding electrons are equally shared because both atoms have the same electronegativity. This only occurs when you have diatomic molecules, meaning H2, F2, O2, because they're the same atom, so they have the same electronegativity and they are equally sharing the electrons. A polar covalent bond is when you have two different nonmetals, and this is when there is unequal sharing of the electrons because one atom is more electronegative than the other. And we looked at this new symbol, this delta positive and delta negative, and that stands for relatively positive and relatively negative, meaning that one atom is going to be relatively negative to the other because the electrons are going to be hanging out more with it, and so it's going to have roughly more electrons than protons. We're not going to put a -1 or a +1 sign like we would for ions, because in an ion the electrons are there permanently. This is a covalent bond, so they're being shared, but the sharing is unequal, so the electrons are going to be spending more time with one atom than the other. So as I said earlier, if you're looking to figure out whether an entire molecule is polar or not, you have to look at all of the bonds. So when a molecule is made of two or more bonds, this is a little more complicated. We have to look at the arrangement of all of the relatively positive and relatively negative atoms, and we have to analyze where they are to see if the whole molecule is polar or not. If the molecule can be turned so that all of the relatively negative atoms are on one side and all of the relatively positive atoms are on the other, then the whole molecule is polar. And again, polar means there's a north pole and a south pole like the Earth, or there's a positive pole or a negative pole like in a magnetic field. So for example, CO2. First, in order to figure this out, we did the Lewis dot structure to figure out that there were double bonds on either side of the carbon, and then we drew it in its three-dimensional shape, which is linear, and that is very important. You have to draw these in the three-dimensional shape. So once we have figured out what this atom is going to look like in three-dimensional space, now we can analyze using our trends in electronegativity, or Fonkelbrish for short, and we can see that oxygen is the more electronegative because it comes first in Fonkelbrish, and so each of the O's is more electronegative than the carbon. So each oxygen is relatively negative, where the carbon is going to be relatively positive, because the shared electrons here between this carbon and the oxygen on the left are going to be heading away from the carbon towards the O. Likewise, on the other side, they're going to be heading away from carbon towards the O on the right, leaving the carbon relatively positive. So because we see that the positive is in the middle and the negative is on either left and right, there's no way that we can orient this molecule so that one side of it is plus and one side is negative. So this is going to be a nonpolar molecule. In this second example, water, we can look at the different atoms after we have determined what is the Lewis dot structure, and then we put the molecule in its bent shape, and now we can look at the partially positive and partially negative. Between oxygen and hydrogen, oxygen is the more electronegative, which means it's going to be the relatively negative of the two. Hydrogen is less electronegative, so it's going to have the relatively positive symbol. And yes, we can orient this molecule, we can rotate it so that the oxygen is on one side, so all of the relatively negative is on one side, and all of the relatively positive is on the other. So this is a polar molecule, and that means we have a north pole and a south pole, or a negative pole and a positive pole. So what does it mean for something to be a polar molecule? It means that it is going to have a dipole moment, which is a direction in which the polar molecule will align itself in a magnetic field. So if we were to put water into a magnetic field or an electric field, we would find that all of the water would orient itself in one particular direction. And that direction is determined and noted with this arrow here. So the arrow always shows the general direction in which the negative electron or the negative side of the pole is, and the little plus at the other end denotes the positive side of the pole. Let me show you this in a three-dimensional model. Here we're going to take a look at this PhET virtual animation sort of thing to look at the molecules. So if we look at water here, we have hydrogen number 1 and hydrogen number 2, and the oxygen. Again, we know it's bent, so we've drawn it in the bent shape. Now, the arrows, as we just talked about, for each bond, we are going to draw them one between this hydrogen, hydrogen number 2, and oxygen is pointing from hydrogen to oxygen, so we can see there's a little plus end of the arrow, and it's pointing towards the negative side. Likewise, for the other bond between hydrogen 1 and oxygen, we see that arrow superimposed, and here's a little plus sign showing that this hydrogen, hydrogen 1, is the positive end of the bond, and the oxygen is the negative bond. So we've looked at these two arrows show the dipole just for those two bonds. Now we need to look at the overall polarity of the molecule. Do the two dipoles cancel out, or is there an overall positive and negative direction? And we can see that there is. Overall, the positive side is the bottom, the negative side is the top. So this yellow arrow is showing us the overall dipole moment for the water molecule. Now if we put a virtual molecule, and I'm going to make the settings fit that of H2O, we're going to put this in an electric field. So here we have A represents hydrogen 1, C represents hydrogen number 2, so they are less electronegative, and B represents the oxygen, which is more electronegative. We can put in the bond dipoles again, and that was what we had seen when we looked at the actual molecule. And we can put in the molecule dipole, and again we know it's in this direction, and we can turn this electric field or magnetic field on, and we can see how it's going to rotate, and this shows that the positive direction or the positive side of the molecule, and here now we have our partial positive or relatively positive signs, they are attracted to the negative pole of the magnetic field, whereas the partially or relatively negative one, B, is going to be pointing towards the positive pole of the magnetic field. So again, this arrow, the dipole moment arrow, represents the direction in which the molecule is going to be oriented in the electric field or magnetic field. The example of a nonpolar molecule we had looked at was CO2, and here we have carbon in the middle and oxygen 1 and oxygen 2. So individually, the carbon-oxygen bond is a polar bond. So we can put in the arrows, and this is showing that relatively carbon is less electronegative than the oxygen on the left, and so this bond polarity would be pointing towards the oxygen. Likewise for oxygen number 2, the bond polarity would be pointing towards the other oxygen. So they're pointing in opposite directions, which is going to show us that I can't put a molecule dipole arrow in, it won't let me, and that's because this is a non-polar molecule. So overall, we could look at the electron density, and it shows that it's going to be more dense towards the outside as opposed to the inside, but if we were to put this in a magnetic field, it would not align in any particular direction because there is not an overall one side that is positive or negative compared to the other. Let's look at a few more examples. With hydrogen cyanide, we could look at each individual molecule and find that the hydrogen is positive in comparison to the carbon. However, the carbon is positive in comparison to the nitrogen. So this is an interesting case where the carbon is going to be relatively positive to one and negative to the other. So we're going to consider it to be neutral, and we're going to ignore it, which is why I did not write a partially positive or partially negative symbol for it, whereas we did for the nitrogen and the hydrogen. And because we have done these, we can see that this is polar and the direction of the dipole is pointing towards the most negative or relatively negative of the sides. For nitrate, NO3-, we could figure out this would be the pattern of the positives and negatives. And this is overall going to be a non-polar molecule because there is no way that I can rotate this in three-dimensional space to make it so that there is one side is polar and one side is non-polar, or I'm sorry, one side is negative and one side is positive. And that's because this is planar. NH3, however, is trigonal pyramidal, and the nitrogen is going to be sticking up. So we could draw a line just like this, and that would denote that the side sticking up is going to be partially negative, and the hydrogens which are touching the ground, the bottom part of the pyramid, are going to be positive. So this one will align in an electronegative field, or in an electric field. Let's take a look at that. So here's our ammonia NH3 molecule, and we can look at each individual bond. And this is a little messy to see because it's three-dimensional, but what we're looking at is that each bond is pointing from the hydrogen to the nitrogen, and so overall there is a dipole, and so this molecule would align in a magnetic field where the arrow is pointing towards where would be pointing towards the negative field, the negative side of the field. So overall this is a polar molecule because all of the bond dipoles point in a general direction, and that is all up. And so we could say that this is a polar molecule because there is all of the partially positive area, the hydrogens are on the bottom, and the partially negative nitrogen is on the top. In our next example, we have a tetrahedral molecule, carbon tetrahydride. When we put it in its three-dimensional shape, and we will use electronegativity rules to figure out which is the partially or relatively negative and relatively positive atoms, we would see again this is a non-polar molecule because there is no way to rotate this molecule, or there is no way to draw a line to put all of the positives on one side and all of the negatives on the other. But let's look at a second tetrahedral molecule in which two of those hydrogens are replaced with fluorine. Now, this one is this is a polar molecule because you could draw a line and you could separate all of the negative or relatively negative atoms from the relatively positive. So this would be a polar molecule because it would align in an electromagnetic field, and it would align in a certain direction. So we could draw the dipole arrow pointing again from the hydrogen side to the fluorine side, which is roughly kind of like at this diangle. So those are kind of parallel to each other. But the point being that it's not just the shape. So not every tetrahedral molecule is polar or nonpolar, as you saw with this and in the previous example. So you have to look at not only the three-dimensional shape of the molecule, but you have to look at each individual atom to determine how the geometry and the electronegativity is going to be arranged to look for symmetry, or in this case asymmetry. So when you have a molecule and all of the charges are symmetrical, meaning you have an equal distribution of positives and negatives so that you cannot draw a line to separate the positive pole and the negative pole, it'll be nonpolar. But when you have this example where it is an asymmetrical distribution of charge and you can rotate this molecule in such a way as to make it where there is a positive pole and a negative pole, it is polar. So keep in mind that these molecules can rotate and spin in 3D space. So if there is any way that you can draw this molecule that it is polar, then it will be a polar molecule. Here's a few practice problems for you to try. You can pause, draw these, and determine the distribution of positive and negative charge, and these are the answers you would find. Good luck!